సరే సాయి ఉన్నదంటే సార్ నిన్నే కాన్సన్ట్రేట్ చేయండి ఈ పీపీటీ ప్రెజెంటేషన్ తర్వాత ఇస్తాను సో బెటర్ కాన్సన్ట్రేట్ యువర్ స్టార్ ఫోకస్ అండ్ స్టార్ ఏరియాస్
Picture on the slide, and there is a very nice story behind this one. Anybody want to guess me what is that story? So that is a 3-zone CVD instrument, and here we have a beautiful graphene domain. 2 graphene grain connected with 1 gate boundaries. So back in 2015, I was working on chemical sensor, and I was thinking to define or to study the chemical sensing property of individual graphene grain boundary. So then we have this this CVD, and we know very well, like in CVD, if you use precursor like methane and a hydrogen, and you use copper as a catalyst or a substrate, then you can easily grow graphene on the copper. But I spent 1 month, I follow every article recipe, whatever they have provided, in terms of like controlling the flow rate, tuning the temperature, but every time, no graphene on copper. And the reason is that, and even, like, I visited another institute who were expert in synthesis of graphene. And I asked them, how do you do? Then they saw me experiment like you guys have seen today, how to synthesize nanoparticle or nanostructure. Same way I did, and we were confident that we are not making any mistake, and we were just curious why it's happening. So in this one, that's a tube here, and in the tube we should have these 2 blocks, ceramic blocks. And when we were setting up the device, CVD setup, so I took them out. And every time I was running the experiment, so there was no graphene on the copper. One day, just like this, just to see, I clicked the copper. On the bottom, there was a lot of graphene, but on the top, no graphene. And the reason for that was how you tune the microenvironment on the copper surface. And these 2 blocks, they help a lot to have a homogeneous environment in the tube. And if you don't have that one, then whatever the precursors were going inside the tube, that was just taken out by the tube. So there was no graphene flow. And I spent like a couple of months just to figure it out, why I'm not getting graphene. So be careful when you have the recipe from the literature. So be careful for that. So last time we discussed about nanomaterial, am I right? And we talk about different type of material, like a 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional. But these material can also be categorized based on the material, and this can be either carbon-based, metal-based, or you can have semiconductor-based or polymeric nanomaterial. Today we will talk about nanomaterial synthesis. So basically there are 2 approaches. One is bottom-up, second is top-down. And then we will go within these 2 approaches, and we will discuss about bar milling, mechanical and chemical exfoliation, or CVD, and maybe some slides related to electrochemical method and solvothermal method. So as I mentioned, two basic approach, either top-down or bottom-up. The basic concept is from top-down, you have bulk material, you just crush it or you do whatever you want to do and find at the end nanostructure. In second way, you have the precursor or the atoms and simply you just play with those atoms and make nanoparticles. So these are two basic categories how you differentiate in nanomaterial synthesis approaches. Top down and bottom up. So there are different approaches, like you will have physical process, you will have chemical process, and even sometimes you will have this biological process. Like when we talk about physical process, so sputtering and electroexplosion or laser ablation or bulk milling. And when we talk about chemical processing, so there are, like we have different methods, like for example, photoelectrochemical process, solvo or hydrothermal process, and like soldier method. So we will talk about some key methods today to synthesize nanomaterials. The first, top-down approach and ball milling. As I mentioned, it's just simply look like very straightforward. You have bulk material and simply crush that bulk material and finally find the fine powder. But there are different steps, different stages. It goes through from here, like from squeezing stages, then grinding stage, then fracturing, and then you have segmentation of flattened particles, and end of the day you will have this fine powder. That is dynamic balance stage. And here also very kind of like interesting physics. If you can load too much powder into the ball milling, then you cannot get the product that you want. If you have like a very high speed, then also you cannot get whatever you want to have. So there is an optimum condition to get this nanostructure. Like if you have, so there are different, as I mentioned, different parameters that decide how you control the size of these nanoparticles or nanostructure. The first is residence time of material in the mill chamber. So it's obvious, means like if you keep these material for longer time, you will crush them more and you can have a smaller nanoparticle. The second is the size, density, and the number of ball mills. So in the instrument, the size and density and the number of balls also decide the size of these nanoparticles. And the third is nature of ball mill. So depending on hardness of grinding material, you can tune the particle size as well. And again, means feed rate and leveling vessel or rotation speed of the cylinder, that's also helping deciding the size of your nanoparticle. So here you see some schematic here. In case of low speed, so you will not able to crush the material properly. If you have very high speed, then again due to central forces, so they will just simply on the outer ring, and then they will not able to crush the material properly. So this is third one is a normal speed where you can get kind of like optimum condition for material synthesis. And depending on the instrument design, there are different type of like ball milling. For example, planetary ball milling, or tumbler ball milling, or vibration ball milling. Again, the concept remains same. Using the ball, these balls, you want to just simply crush the material. The basic concept remains same. Another two methods, like one is physical vapor deposition, the second is chemical vapor deposition. Both are completely opposite. Physical vapor deposition. So this is kind of like top-down approach. Chemical vapor deposition, it's a bottom-up approach. So in chemical vapor deposition, the process is driven by sputtering or evaporation of physical particles. In second case, the reaction is driven by gas molecules and interaction of those molecules with the substrate. So when we talk about physical vapor deposition, so there are different subcategories like sputter deposition, electron beam deposition, or thermal evaporation deposition, or arc evaporation method, or pulse laser deposition method. So each type of these PVD methods, they are similar in terms of like working mechanism, but they have a different procedure. And when I say different procedure, the way they evaporate these molecules, that technique is different. Otherwise, the mechanism is same. So first one is perfect. So that is the process to produce nanomaterial simply via bombarding solid surface with high energy particle, such as plasma or gas. And that is considered to be an effective method for producing thin film of nanomaterial. In my lab, I have a DC magnetron sputtering tool, and it's very easy to prepare any type of like a thin film or a hybrid film. So even you can create some nanostructure depending on deposition time or depending on like the pressure or the environment that you use. If you have nitrogen here, maybe you can have nitrogen doped material as in place of like a pure material. So it has some limitation. The limitation is that gas atoms may also get deposited on the substrate along with the coating substance. And if that will happen, the quality of the thin film will not be perfect. It may have some porosity or some defective structures. The number 2 is electron beam PVD. So in this process, we use a high-speed electron beam to convert the coating substance into a gas phase. So in previous method, we have these, like either plasma or gas to convert these substance into the gas phase. But in this way, in this case, we have high-speed electron beam. And here, like we have some advantage and some limitation too. The limitation is only lime oxide coating. So if lime is small, so simply you can coat a very small sample. It's like that's the limitation of this one. But talking about this sputtering, even if you can coat a 4-inch wafer homogeneously all over the surface. So that's how that feeling. Thermal evaporation PVD. In place of electron beam, now we are using a simple temperature, and you can increase the temperature by using different method. So if you use any filament to heat and evaporate the coating substrate into the vacuum chamber, and then these kind of like atoms will be deposited on the substrate. Again, it has some limitation. The one is complex structure cannot be coated. When I say complex structure, like if you want to precisely control one section of any device and not the second one. So there are some limitations for this one. That's another method, pulse laser deposition method. So as you see by name, here we have a pulses of the laser to simply evaporate those atoms. And it's like a relatively new process, and this process is still in developing phase. But the beauty of this process is that you can have really very high quality of film, very high quality of thin film. You have a great control on that one. Here we are talking about graphene synthesis via sublimation and exfoliation. Again, both methods, they are top-down approach. When I say sublimation, so in this case, simply you may have, like a bulk silicon carbide material, and then you will heat it at very high temperature. And depending on the top layer, it's a silicon or it's a carbon phase. If it is a silicon phase, carbon will diffuse slowly, and you may have just only one atom layer on the substrate. But if you have carbon phase on the top, then you may have a multi-layer of graphene on the substrate. And that process is also very good in terms of like controlling the quality of graphene. The second is liquid phase exfoliation of graphene. Again, here you will use the bulk graphite, and then using exfoliation method providing energy in the form of vibration, you can break that graphite into the graphene layers. And depending on the like a weight, you can collect different size of these graphene layers. Like you may have monolayer, you may have bilayer, or you may have multi-layers. So flake thickness, distribution, like based on that one, you can collect it. But it's very cheap, inexpensive method. You can like easily do that one at bulk scale. Recently, we have one report. I don't know if you guys have read that one or not. In 2025 only, couple of days back. So the scientists, they designed a method, and that method is kind of like a universal. So what they have done, they have a gold layer, and when this gold layer interact with any bulk material that have 2D structure, so the interaction of the gold layer with that substrate or that material is stronger than interaction of two thin layers. Like for example, graphite. The interaction of graphene and graphene in graphite is weaker than the interaction of gold and graphene. So what will happen if you put that on top of graphite? You will have a layer of graphene on the bottom. Am I right? And doesn't matter what material you will have 2D material from the periodic table. They are able to have 52 different type of 2D material using this method. And the title is Universal Mechanical Exfoliation of Large Area 2D Crystal. So that's very straightforward, chemical free, there is no chemical, there is no need to have high temperature, high vacuum, there is no need to have any specific instrument. If you have the two things, a thin layer of gold on substrate and your bulk material, simply with physical kind of like contact, you can extract a single layer of that 2D material. And here is the graph that's showing the higher energy of gold with those 2D crystals. Very unique approach. And here, this is the kind of like process how they have done. So first, you have the substrate. On the substrate, you deposit a gold thin film, and then you have the bulk material. So for example, here you have these NOS2, and then just simply on the top you put a tape, and on the bottom you have this gold film, and finally you have a monolayer on the gold. And if you compare this thin film quality with chemical vapor deposition or mechanical exfoliated grown MOS2, it is much, much better. And size is also pretty big. And the beauty is that you can get any 2D material using this approach without any chemical or without any chemistry. There is another method that is called vapor liquid solid method. Basically, this method is particular to grow nano wire with the vertically grown nanowire. So here, the chemistry is here. You have these kind of like liquid drop of metal, and then the reaction will happen. So on the bottom, you have these metal oxide nanowire, and on the top you will have these liquid metal droplet. And the electron and oxygen recipe, they will go through this one, and the wire will be gone. And here the condition is that temperature of substrate should be higher than temperature melting of the metal. That's the condition here. So that was about kind of like top-down approach, and the best is mechanical exfoliation, the recently that article published. The second is chemical vapor deposition. Again, look like very simple technique. It has 3 steps. Like first is precursor injection, and then reaction site, and then gas ejection module here. So 3 sections here. So like for example, to grow the graphene, you have methane, hydrogen, and argon. And then you have this tube. In the tube, you have this copper foil here, and you flow this precursor in the tube. And at this side, you have a vacuum pump to take out these, like whatever the precursor, remaining precursor is there. And there's a simple video about this one. I don't know if it will work here or not. What is that? Anyway, that's fine. But I have one more video here. So you can check. That's fine. That's okay. So the link is not working here, but I will share the video with you guys. So chemical vapor deposition method that can further classify in atmospheric pressure CVD or low pressure CVD and ultra high vacuum CVD. Just give you an example about these 2 technology. The first one, atmospheric pressure and low pressure. So if you want to grow graphene using these 2 technology, for example, when you use low pressure technology, it's very hard to have a monolayer graphene layer. But in the first case, at constant pressure, CVD, you can easily get a single layer graphene. And then you have these aerosol assisted CVD or direct liquid injection CVD or metal organic CVD. And this MOCVD, that is called metal organic precursor, actually used here. And that's widely used to grow the synthetic diamond. This is how the chemical vapor deposition process happens. So in first phase, you have diffusion of precursor, and then in second phase, you have absorption on the surface, and then you will have desorption of absorbed material, and then they will diffuse through the vacuum here. So total 5 steps here: diffusion of precursor, absorption on the surface, and then chemical reaction, surface diffusion, and desorption of absorbed material, and finally diffusion of byproduct. And that's here boundary layer. So under the boundary layer, you have this surface reaction, and on the top, you have these active precursor here. This is in more detail like what you should consider here. For example, mass transport, gas diffusion, or intermediate reactants, how they interact, or desorption and mass transport for the byproduct. So all these play very, very important role to control the quality of graphene or to control the quality of your 2D material. And that was the reason when I don't have those ceramic block on both sides, so I was not able to control all these processes properly. Again, means depending on external stimulus, CVD can be classified further plasma enhanced CVD or hot filament CVD or rapid thermal CVD. As you know, like by name you can see, in plasma enhanced CVD, you use plasma technology with CVD to enhance the process. And in third one, rapid thermal CVD process, you will use a rapid heating to heat the substrate and improve the reaction on the substrate surface. And here, this is one example about high density plasma enhanced chemical vapor deposition method. And it will have basically two power sources. So one may be capacitively coupled plasma, or the second is inductively coupled plasma. So you can use any one of these sources to create the plasma, and then you will have these, like a high density of plasma to enhance your chemical vapor deposition process. The one more important parameter here when we talk about chemical vapor deposition process, at what time you wanna turn it off, or at what time you wanna release or turn off one precursor. So for example, in case of like graphene, if you are continuously flowing methane and hydrogen, and just you turn off your experiment in same condition, maybe you will end up a defective graphene or a multi-layer graphene. Because at the last stage, still you have methane precursor to interact with your substrate. But if you turn off the methane precursor first and then let the hydrogen flow, then you have a better quality of graphene. Because hydrogen will clean the surface and remove the impurities, whatever you have physically absorbed or relatively weakly absorbed methane precursor there. So that's also very, very important condition that we should consider. Particularly for the graphene synthesis, the substrate also play very, very important role. And basically two different types of substrate we use. One is copper, the second is nickel. So nickel has a more carbon solubility. So when it has a more carbon solubility, so it has a thick layer of graphene on top of this one. But for the copper, the solubility of carbon is not much, or it's less than the nickel. So that's why on the copper you can have a single layer or bilayer of the graphene. So here you can see the process, different steps for the nickel catalyst and in the case of copper catalyst. So in the nickel catalyst, like decomposition of your precursor will happen, then dehydrogenation and the bulk diffusion through the sample, and then segregation will happen, and then finally you have nucleation and the drop. But in case of like copper, the surface migration of L atom, that's play a very important role to grow the graphene there. And here is the kind of like the reason between these two substrates. Like in first case, the copper sublimation triggered carbon evaporation at around 4 eV, and the nucleation happened around at 9 eV volt. And based on this one, even you can have a seeded growth of graphene. So if already you have a graphene kind of like tiny particle on copper on any substrate, so due to this add atom process, you can increase the size of that pre-deposited graphene. That is called seed growth of graphene. Here there are some improvements, like in place of using the pure copper or a solid copper, the copper is melted, and then on melted copper, people have grown the graphene. And in this case, they were able to get very, very high quality of grain. These, as you see in the SEM, these hexagonal shapes, they are kind of like graphene grain here. That's a kind of like pretty straightforward process for high quality graphene process. One more advantage about CVD method, like you can control the material that you wanna design or you wanna fabricate. For example, if you have graphene and you need some part of the graphene, then you can deposit a second material here. So you can have a hybrid structure. Either it's lateral or it's a vertical, doesn't matter, but in all way you can have a different type of unique structure using the CVD method. So when we are talking about this carbon material, so after growth, transfer process is very, very important. So there are different transfer processes. The straightforward is first one, like you have graphene on the copper, and then you will fix to a glass slide, then spin coat a polymer, and then remove from glass side and put into a kind of like reducing agent or the liquid there, and then copper will be dissolved, and finally you have graphene on PMMA, and then you can deposit that graphene on any substrate wherever you want, and then you can fabricate your device. But in that case, we have the quality of graphene is not really good. Either we have impurities, despite like a multiple cleaning process, still we may have some impurities there. So to overcome that, there are kind of like semi-dry process or a simple wet. So in comparison these two, so semi-dry process is better than wet transfer method. Here in this case, you have a better quality of graphene compared to this one. But still, we can solve the problem to have pure graphene, and that can be done using completely dry graphene transfer method. So in this case, we don't have any agent, we don't have any additional reactant or any additional molecule to interact with graphene. So finally, end of the day, you will have relatively very pure graphene that cannot be attained with simple kind of like wet transfer method. So here you can see in this case there is no wrinkle, no any kind of like extra particle, but here you can see a lot of wrinkle, a lot of defects here. That was about CVD. You can use graphene and follow the 2D material too. There is one example about NOS2. But here, the difference here and the previous one, in previous one, we have a gas-phase precursor. But in this case, we don't have a gas-phase precursor. Basically, we have these kind of like first MO container, and then here sulfur container. So we have these two containers here. So first, sulfur will be evaporated, and then it will pass to the tube and will interact with MO and will deposit on the substrate. So you see here temperature first 200 degrees Celsius, then 500 degrees Celsius, then 800 degrees Celsius. So it starts from here and go through this process. And finally on the substrate, you may have either monolayer, bilayer of these MOS2. And this technique can be used for different type of these PMDC material. The chemical method. Today you learned a little bit chemical method in the lab, and you synthesize zinc nanowire or nanoparticle that we don't know, but you did something, right? So for the chemical method, so it's a straightforward process here. First you have precursor activation, then nucleation, and after nucleation you have two processes, either oriented attachment or atom by atom attachment. So in these two processes, finally end of the day, you have this nanocluster or nanoparticle here. And on the bottom you can see the size. The metal precursor size is around 0.1 nanometer, and then seeds and cluster, they may be 1 nanometer, and then metal nanoparticle, they may be 10 nanometer to 100 nanometer. So depending on at which stage are you, you can have different type of size of these particles. This is a colloidal synthesis method. I think in last presentation we discussed that was discovered in a very old time, and it's a very straightforward way. So first step is nucleation here. The second step is growth by aggregation, and then third step is slow further growth here, and the fourth step further fast growth, and you will have a big nanoparticle here. But here in this case, couple of challenges. One is how you can put a particular nanoparticle at a particular place. So that's one challenge. The second challenge here is how to precisely control the size of these particles. So at least we have these two basic challenges in case of this colloidal synthesis method. So to have these nanoparticle at particular place, so you can play with some chemistry here. So like in first case, we have this gold precursor in the liquid, and on the substrate, we do have these strong reductant. So this gold precursor, they will interact with those reductant, and reduction reaction will happen at that particular position, and then you will be able to have that nanoparticle at that particular position. So here are three different conditions. In first case, you have a strong reductant in solution and a strong reductant on substrate. In second case, you can have a strong reductant only on the substrate. So all reduction reaction will happen on the substrate. In third case, you will have weak reductant in solution and a strong reductant on the substrate. So in solution itself, you may have a tiny particle due to this weak reductant. And when it will go to the substrate, then you will have a strong reaction, and then you will have a control growth of this nanoparticle. And here you can use, like an in situ chemical surface growth of metal nanoparticle as well. So when we talk about metal nanoparticle, there is a one parameter, that's size. Second parameter, the shape. Third parameter is crystal. So what type of crystal do you have? It's 111 or 1100, etc. like that. So you can control those things using in situ seed growth. So in this case, depending on what you have initially, you can have a particular type of crystal structure or particular type of shape. Electrochemical method, that's a very simple method, and it has a pretty good, a way to grow well-designed or controlled nanowire. So in that case, what you need to do, simply you will have these aluminum kind of like a membrane, and it has these vertical tube. And during electrochemical deposition method, these tubes, they will be filled with the metal particles, and finally you will each AAO, and then you will have these vertically drawn nanowires. And the beauty of this method is that you can do one electrochemical deposition at one time with one precursor, and then you can do second step with second precursor. So you can have a hybrid structure here, or you can tune the material property by just using, like electrochemical pulses. For example, do that for 10-second deposition, and then again do 10-second deposition material B. So then you will have a pretty hybrid structure. This is just only one example here. This electrochemical deposition method can be used for any substrate. Doesn't matter what type of conductive substrate you do have. Either it's graphene or carbon paper, anything, whatever you do have. Simply put into the electrochemical cell, apply a potential in presence of precursor, and then you will have some deposited material. This is aluminum oxide membrane. This is actually kind of like a predefined structure. So it has pore and it's made of aluminum. And so these pores are filled with the metal when you do electrochemical process. And then finally you just etch it away. Yeah, it's just like a substrate. Solvothermal method, a very simple strategy here. You have this a simple vessel, and that vessel can contain very high temperature and very high pressure. That's the beauty of this vessel. And this vessel is filled with precursor, and simply you will heat it, and then after heating, you will take it out the material, clean it, or use the reducing agent if you want to do further, and then finally you will have, for example here, either nanoparticle in the solution or nanowire in the solution, and then you can use kind of like different process to have these nanowire on your substrate. So very simple method, and it doesn't need any specific tools for any specific instrument, except this vessel and maybe one furnace. That's all. Those two things you need. Here are a comparison for different methods. So what are the pros and cons? For example, chemical vapor deposition, it has advantage because it has high deposition rate and high purity, and like if you want to have any product for commercial application, then CVD is pretty good one. But it has some issue as well, because to synthesize multi-component material is really difficult, and it lacks volatile, non-toxic, and especially for thermally activated CVD. So they may have these volatile or toxic precursor there. Template assisted growth. So the pro of this method is you have control, very precise control over the structure of the metal oxide nanowire. But you need to remove that template. That's only one drawback here. Then you have electrochemical deposition method. So electrochemical deposition method you can do at room temperature without any problem. And it has, you can control the thickness of the film, you can control the deposition rate, but the problem is that all materials cannot be deposited using electrochemical deposition method. And the broad substrate must be conductive. If it is not conductive, then you cannot run any electrochemical reaction. As I mentioned, solvothermal method, low cost, very simple one, but it needs organic solvent, and definitely you will need higher reaction temperature and pressure too. Talking about graphene, so here is a timeline of the synthesis related landmarks for the graphene. The first one, 2004, that was epitaxial growth of fuel air graphene. Maybe you need to do that experiment at your home or in the lab. What they have done, they use a simple tape, and on the tape they put the graphite, and simply just they do multiple times like this. And finally they end up with a single layer of graphene. But that was very hard task, because on the tape you have a single layer somewhere you have double layer or multi-layer. So it was very hard task to locate the single layer graphene on the substrate and fabricate a device. Then in 2006, we have this epitaxial graphene on silicon carbide. Here we use sublimation method, and the beauty of this approach is that you can control the number of layers of graphene on silicon substrate. The drawback is there, it's very difficult to take out graphene from silicon carbide substrate because it's very, very strongly bonded to the substrate. Then in 2009, we have the CVD graphene or Ni catalyst or the Cu catalyst, or even like Ni and Cu carbon isotope or PT catalyst. Then in 2011, we have roll-to-roll CVD production. So that's provide you capability to produce graphene at large scale for your industrial application. And we do have a laser ablation method to produce graphene sheets, and these were relatively pure. But one major breakthrough happened in 2020, where we have this flash graphene. And the approach is here in this case. In the furnace, you have this bulk graphite, and simply you just apply very high voltage in the form of the pulse to create really very high temperature, and it just explodes the graphite into graphene. So there is no chemical, and finally you end up a large amount of graphene using this method. That's kind of like one method for the commercial application too. This is about to have graphene from graphene oxide. So the first method is, this Brodin method, and then Hammers methods. They were very old, 1958. We use very harsh chemical there, like sulfuric acid. And then we have modified Hammers method. So in modified Hammers method, we use same acid as a reducing agent, but we just change, the second step, where we go for like TMNO4 to convert this graphene oxide into the graphene. Then this graphene oxide can be reduced into the graphene using different process, either hydrogen reduction or hydrothermal reduction, or even UV radiation or solar reduction. So there are different reduction approaches to convert graphene oxide into the graphene. Now, comparison of different methods for graphene production. If you want to produce graphene at a larger scale, so you will see different parameters. One is graphene quality, the cost aspect. So here in this graph, cost aspect, a low value corresponds to high cost of the production. Then the scalability, purity, and age. So here it's a comparison for different methods. So for example, when we synthesize graphene on SiC here, so you see G is at 3. So it means quality of graphene is the best, very highest quality of graphene. But yield is very low, scalability is very low, and cost is very, very, very high. And when you have this reduction of graphene oxide method, yield is really very good, but the quality of the graphene is not good. It's for scalable, if you can have like for industrial application, but quality is really very poor. Then you have this mechanical exfoliation, for example. The quality of graphene is great, but chance of scalability is almost 0. So you need to find out the method that you are looking for your application. If you want to have really very high quality of graphene, then maybe you will prefer mechanical exfoliation or synthesis of graphene on SiC, or maybe this one. But if you want to have a little bit larger volume of graphene, maybe you will go for reduction of graphene oxide here. So you will have a larger amount of graphene here. Some application of the graphene, there are many applications of the graphene. And for example, means graphene coating on the substrate, graphene can be used in lubricant, and graphene can be used in batteries, for solar cell. So many applications of the graphene in the many things. But one here for the sensing application, because you are interested for sensing. So this is a very interesting application of graphene, especially it happened during the COVID. So people have created a graphene-based field effect transducer or a sensor. And here they grafted graphene with SARS-CoV-2 spike antibody, and that was able to detect COVID very quickly. So immediately you know that you have COVID or not, depending on this. The second is for medical application. For example, you have these nanowire, and on the nanowire you can attach any kind of like these, for example, peptide or drug-loaded nanowire-based scaffold. You can put on the bond, and then bond recreation can happen here. So in the medical application, you can use this nanostructure. Here it's about energy application. So you can see graphene is on the top here. So in future, I think graphene will lead in the energy sector because it has a great potential to overcome the limitation that we do have with other materials. And with that, thank you. Any question? Anybody has any question? The floor is open for you now.
Thank you very much, sir. It's a wonderful presentation. Can you shed more light on the dye transfer technique of the graphene?
What is that?
Dye transfer technique. Can you explain more about this? Yeah. This one.
Yeah. So here, in first step, you have one adhesive strange layer on the top of graphene, and if graphene is on the copper, for example, then you have one adhesive layer on the top of the graphene. Then simply you will take it off, then the graphene will be on your that adhesive layer. That's your second step. And then you can put it wherever you want to put, and then go for this thermal release of the tape. You know, like increase the temperature, tape you can take it off, and then simply you have graphene on the substrate. And if there are some impurities, you can again heat it, anneal it in presence of argon. So if there is any contamination due to this adhesive tape, that will be gone. Anything else? I think you guys were sleeping, right?
Yes, sir.
So no question. Cool. Thank you then.
Okay, everyone, it's time for the quiz now. I will share Presenter continue.
Loading. I don't that remote is not being used. And you can have the PPT on the didn't get how you to dealing okay va அது வந்து நமக்கு கொடுப்பாங்க இங்க லைட் அதுதானே ஒர்க் இப்படி வச்சு லைவ் அது கொஞ்சம்
Anybody still writing the quiz?
Solvents for composite material. Graphene is the strongest.
At least any one of them. He's just giving the parents what's a general overview. Not allowing it to take continuously giving the parents.
Graphene is the strongest material known to humankind. It is made up of a single layer of carbon atoms that resemble chicken wire. A tiny amount can significantly enhance the properties of plastics, paints, composites, asphalt, wood composites, concrete, metals, and even lubricants. Until now, Graphene has been expensive to make, limiting its use in large industrial applications. Rice University researchers discovered a process that can start with almost any carbon source, including coal, petroleum coke, mixed plastic waste, rubber tires, biomass, and even waste food, and convert it into graphene. The procedure uses no solvent and no chemical additives. By placing any solid carbon material between two electrodes and applying 200 volts in a short electrical pulse, the temperature instantaneously heats to almost 3000 degrees centigrade, and every chemical bond in the material breaks. The non-carbon elements sublime out, and the remaining carbon atoms reconstruct into graphene. All in a bright flash of light in less than 1 second. The flash process happens so fast that the surrounding container does not even get hot. The flash process is the first bulk process to produce what is called turbostratic graphene, as opposed to the more common A-B step graphene that is made by graphite exfoliation. The typical graphite-derived AB arrangement makes it hard to pry apart the graphene layers. But in turbostratic graphene, there is no ordered alignment between the graphene layers, making the layers easy to disperse in solvents or composite materials, and thereby rendering the excellent graphene properties to the composite at ultra-low turbostratic graphene concentrations. For example, by adding less than 0.02% of turbostratic graphene to concrete, it increases the concrete strength by 35%. This means we could use much less concrete to achieve the same structural integrity. Not only can turbostratic graphene strengthen structural materials, it can also have a huge environmental impact. It provides a new use for coal without the need to burn it. It leverages materials that would otherwise end up in landfills. It converts biomass that would otherwise decompose. It allows us to use less of the expensive materials we use today, and all this will reduce our carbon footprint and lower greenhouse gas emissions. The flash graphene process also fulfills all 12 principles of Greek chemistry. Turbostratic graphene is a major technology breakthrough, all made in a flash.
I hope you enjoyed today's workshop. I request everyone to have tea and snacks, and that's it for today. Thank you.